Hey everyone, I just wanted to share with you something from the calculus of variations, and this is going to serve as an introduction to Lagrangian mechanics. But first, we have a very important equation to derive. So, say you wanted to find the minimum distance between 2 points. Well, you'd probably tell me, oh, that's just a straight line. But how would you prove that? Well, you use something called the calculus of variations. The length of a line that can be described as a function of x. So, like, for example, if this were the x-axis and this were the y-axis, we can describe it, and you may remember this from calculus, is 1 plus y prime. Dot means with respect derivative with respect to x, y prime of x squared with respect to x, and that's the distance between those 2 points. But how do we minimize this integral? Well, you would want to find a value that is stationary, so the derivative of the length with respect to some sort of variable is going to be equal to 0. And that variable represents the deviation in path. So if we were to generalize this to some different sort of integral, what we could do is we would find some j that varies by some parameter alpha of a function from x1 to x2, and we'll call that function f of y, which is a function of x and alpha, y prime, which is a function of x and alpha, and x, which is just an independent variable. And we take the integral of that with respect to x. So to find a stationary value of j alpha, what we would want is we would want the derivative of j with respect to alpha at some point alpha equals 0, because we're going to assume that alpha equals 0 is the correct path. So alpha equals 0 is going to be equal to 0, and that's what a stationary point is in calculus. So to do that, what we can do is we could take the derivative of, well, both sides of the equation. And to do this, we have some special rules when we're taking a derivative with respect to a variable that is not the variable of the integral. So what I mean by that is, like, we're taking the derivative with respect to alpha while this integral is with respect to x. And the way that we would evaluate that is still an integral from x2 to x1, but this time we take the partial derivative of f with respect to y, and we multiply it by the partial derivative of y with respect to alpha. So partial derivative just means that you're going to treat everything else as a constant. If y prime or x appears in the equation, we're just going to treat that as a constant, and we're only going to take the derivative with respect to y. That's for a multivariable function. And the partial of f with respect to y prime times derivative of y prime with respect to alpha dx. So we can find that this part right here is just df over dy prime times the second derivative of y with respect to x and with respect to alpha, because you'll recall that y prime is just dy dx. So if we take the derivative of y with respect to x and then with respect to alpha, then we get that. And what we can do from this is we can integrate that by parts. So let's say we wanted x2, x1, and then I'll just move this over here. With respect to x, if you integrate that by parts, you're just going to get df over dy prime dy over d alpha from x1 to x2 minus the integral of x1 to x2 of the derivative with respect to x of f over y prime times the derivative of y with respect to alpha, and all of that with respect to x. So one of our conditions was that at alpha equals 0, we're going to, for the correct path, the conditions on all varied curves is that they pass through the points x1, y1, and x2, y2, because we're trying to find the minimum distance between two certain points, and those points are fixed. So that means that this derivative right here is going to vanish at x1 and x2, because there's no difference. No matter what variation of alpha you're going to have, it's not going to change the y-coordinate right here. So at points x1 and x2, that's just going to vanish. So basically we just get rid of this, it just cancels out. And we're left with this integral right here. So what we can do is we can factor out, we can add this back into here, and what we do is we'll just factor out the dy dA. So x2, x1, f over dy minus d over dx, this df over dy prime, and then all of that times dy over d alpha, and all of that with respect to x. Now, something from the calculus of variations that I'm not going to derive or prove today is the fundamental lemma of the calculus of variations, which states that if we have some integrals from x1 to x2, some arbitrary points of m of x times eta of x dx equals 0, for all eta of x that is continuous to a second derivative, such that eta of x1 equals 0, so it just basically vanishes at the endpoints. Eta x2 equals 0. So the fundamental lemma of calculus of variations tells us that if these conditions are met and this condition is met, then m of x is going to be equal to 0 for all x in the relevant interval. So what we can do here is, well, this function right here is going to vanish at the endpoints, so that can be our eta of x, and then this function right here, and then this is going to be equal to 0 at alpha equals 0, right? Because we said that we want dj over d alpha to be 0. So what that means by the fundamental lemma of calculus variations is that this part right here is going to be equal to 0. So if we rearrange that, we get something called the Euler-Lagrange equation, which is very important in the calculus of variations, as well as in physics in general, as we'll see in future videos. And basically what that states is that this quantity is going to be equal to 0. And the way that we can apply this to our length equation, we have L equals from x1, x2, 1 plus y prime squared dx. Well, we want to minimize this length. So what we can do is we could say that, well, our f of x here is just going to be the integrand. So not our f of x, our f of y prime, and x. So f equals the square root of 1 plus y prime squared. And then if we're just going to evaluate every derivative in here, we get partial f over partial y is just going to be equal to 0 because, as you'll notice, y does not appear anywhere in the equation for f. And then partial f times partial y prime is just y prime over square root of 1 plus y squared. Therefore, d over dx df of this y prime square root 1 plus y prime squared is equal to 0. So if we integrate this on both sides, we'll just see that this quantity right here is constant, which just means that y prime is constant. You can do the algebra for that if you want. But what that leads us to is, well, y prime is constant, right? So we can just call that constant m, and then we can take the integral with respect to x on both sides. So y equals mx, and then our constant of integration, we'll just call that b. So what we've used is, well, we used the Euler-Lagrange equation to prove that y equals mx plus b is going to minimize the length between 2 points. So basically, the minimum length between 2 points is a straight line.